Hi and welcome to this video about my Homebrew computer, which today is about devices and controlling different devices and redirecting outputs from one device to another device. The computer, the Homebrew that I've got, supports three devices: serial, screen and keyboard, and SD card. Basically, you can read or write through any of these devices. But what I've also got is at the higher level software, I've added a feature to be able to define which device I want to do print or input from. So normally when I type print line, I say hello. It's gone in caps, but anyway, it doesn't matter. It's going to print hello. But now what I can do, and you can see on the large screen, I've got a serial terminal. So I've just got TerraTerm running here at 19,200 baud connected to the Homebrew, and device 0 is the serial port. So if I was to type here, and I type hello serial, so we can see it's definitely a different message. And then I need to reset the device to -1, which is back to the default device. Now watch the serial window here. You'll see that when I type enter, press enter, I see hello serial on the serial screen and nothing on the actual TV monitor, which is exactly as I would expect. I can do the same with SD card, which I won't demonstrate here, because with an SD card you first have to open the particular file stream that you want access to, either to create a new file or to read an existing file. And then print will work fine actually. I can even do inputs, as I mentioned. So if I type device 0 to go to the serial port and ask for input A, and then go back to my default device, which is screen and keyboard, and then print the value that was captured, then you can see if I go to the serial device, I'm going to type a number. 1, 3, 4, 6, and press enter. And 1, 3, 4, 6. I didn't do the CR on the screen. Doesn't matter. 1, 3, 4, 6, as you can see, has been captured from the serial port and then translated into a number. So this is really useful because, as I said, I'll be able to programmatically take input from one device and redirect it as output to another device, etc. And in particular, what I thought I'd be able to do is to implement an XMODEM protocol. So XMODEM is a protocol from 1977 suited for small computers like this Homebrew. And the structure of XMODEM is that you have a header of your, before your payload of 128 bytes, you have a header byte and two block number bytes. So you read those, and if the header is a certain value, then you read the rest of the payload. But if the header is a terminating value, then you can stop. So it means that I need to poll the serial port, or I need to read the serial port and then check the header and then read the rest of the bytes. However, in my implementation, in my first implementation, which I've had working fine for absolutely yonks, the serial port is attached to the serial chip, which is a 6551. It's this one here. That's the chip here, 6551, serial input output chip, and it doesn't have any buffers, but I didn't think I needed buffers. I felt that I could go and get input when I wanted it and just poll for input, and this has been working fine and it's been completely suitable for my needs. However, with XMODEM, if I want to read a byte and then do anything with it, like save it somewhere or even look at it and then read another byte, you have to do that extremely rapidly, otherwise you lose data, because at 19,200 bits per second, roughly 10 bits per byte. That's basically nearly 2,000 characters per second that the sender on the PC side could be transmitting, and dflat can't keep up. Even though it's a reasonably fast interpreter, and it's running on a 5.5 megahertz 6502, which makes it very, very nippy. Even so, it's nowhere near quick enough, or it's not quite quick enough to receive all the bytes that are coming down the serial line through polling and not lose anything. So my only option therefore was to implement a FIFO, a first in first out buffer. I already had the space allocated for this in my memory map. I just never thought I'd need it. So when you go from polling to a buffer, what that means is that you actually also have to not poll, you have to be able to receive data when the data is available. So now you have to move to an interrupt based system. So the 6551 does support that. And what I had to do firstly is to redesign or re-implement a bit of hardware here. It's very simple actually, but this purple line, I'm just touching my pen, is the interrupt request line from the 6551, and that goes into the non-maskable interrupt of the 6502. The 6502 has two levels of interrupts, one called IRQ and the other one called NMI. And the NMI, the non-maskable interrupt, it was going spare, so I decided to use it. And I also found, just one quick point, is that I needed this thing here. I don't know if you can see it very well, but I had to basically implement or put a pull-up, a weak pull-up 470 ohm resistor there tied high to keep the voltage high until the chip wanted to signal an interrupt. And I want to just show you what that looks like. So when an interrupt occurs, this is the non-maskable interrupt line. You can see it's 5 volts basically, so this is 2 volts per division, a little bit noisy, 5 volts, and then an interrupt occurs because some data has been received by the 6551, and the line goes low. Now the software interrupt handler kicks in. It does a bit of work to get to the interrupt handler, takes a few cycles, and then one of the first things I do is to reset the interrupt bit. So then the interrupt signal goes high again to signify no interrupt, or the interrupt being serviced at least. And that takes nearly 7 microseconds actually. It's quite a few clock cycles just to be able to do that. It's 5.5 megahertz 6502, so yeah, it's taking 20-30 clocks instructions to do that reset, which is plenty fast enough to service a 19,200 baud serial line. So that shows and that's what I'm showing here basically. This is just the probe attached to the same non-maskable interrupt line. So that's what we're seeing there. So then what does that result in? Well, what we have to do is receive the in the interrupt handler, receive the data byte and put it into the next available position in the buffer. And it's a first in first out buffer, so you have to have a pointer to the first and a pointer to the last. And so essentially I'm adding to the last available position, then I'm updating that pointer. And I can show you that because obviously I know all the locations of my code. So if I print peak 14, that's the available, that's the first position in the buffer, and then 15 is the last position in the buffer, and then if I not next until 0, so I'll just keep looping forever, but I have to obviously type it correctly. I didn't type print. and this is all doing in real time, so sorry for that. Okay, all right, so I've already been typing things, which is why it's on position 5. It's normally at 0, but you can see the serial line here, the serial window. I'm now typing. If I type something like hello, this is 6502 nerd. What you can see is each time I typed a character, the position called last was being updated. So it's now at position 27. So 5 is the first byte in the buffer, 27 is the last byte. So that means there are bytes in the buffer that haven't been processed by the computer, by the Homebrew. Can I access those bytes? Yes, I can. So if I now go to device 0, which is the serial buffer, and then get a character from the serial buffer, I've got, to get a single character, it's called key 1. Sorry. 0 means asynchronous, meaning it doesn't block. So it will either return a value in C or return 0 if there was no value to return. So it's a non-blocking call. And then I'm going to print that to device -1, which is my default device. And so let's print it without a carriage return. And then until C is equal to 0. And then make sure my device is at -1. It will be, but this is just extra cautious. Now what we should see is essentially those characters that were acquired by the buffer that we couldn't see, that I was typing on the serial, on the terminal, on the PC. So let's see what happens. And you can see there, hello, this is 6502 nerd, and there's no carriage return, so that's the computer's own ready prompt. So that's pretty cool. What that means is that the buffer is collecting in the background while I'm working away or doing other things in the foreground. The buffer is able to collect 255 characters, or 256 actually. So 256 characters multiplied by 1,920 characters per second gives me, if my calculations are correct, 1920 divided by 256 gives me up to, I know it's the other way around, isn't it? So 1 divided by 1920 is 0.0052, and if I multiply that by 256, that means I've got up to 0.13 seconds worth of buffer before the buffer overflows. So as long as dflat can poll characters off the buffer within 0.1 seconds, which is not a lot of time, but enough time, then I should be good. So that means I can implement an XMODEM protocol, which I want to show you, but this video is already 13 minutes long. But let me just load this up, and I want to show you very, very quickly some lines from the program. And you can see here I'm calling device 0 and I'm doing various printing, etc. But I'm not going to show you this program right now because I'd like to explain the protocol as well as show this running. But yeah, it's been a bit of a journey to be able to implement XMODEM. I had to go back and fundamentally redesign the serial input and outputs, the serial inputs design, so that it was interrupt based rather than polling based, and using a FIFO buffer. So that was quite a bit of a change, but actually luckily I built the software in quite a modular way, so it wasn't a huge change in terms of the overall effort. So thank you for watching this video. It's a very long one, it's 15 minutes, but I hope it made some kind of sense, or at least gave you something interesting to find out about.